Good afternoon, ladies and gentlemen. It's my pleasure to start the second day of our section with the talk of Miguel Berbel, who will speak about Lagrangian reduction by stage from mechanics to field theory. So 30 minutes, please.
Okay. Thank you very much for the introduction. I would like to thank all the organizers for these amazing days in Hradec and also for the opportunity to be sharing my work and the work of Marco Castellón here in this talk. Well, we can start by seeing the title, Lagrangian reduction by stages. So I'm going to be explaining reduction in the Lagrangian side. That means that I'm going to be using the symmetry of a system to obtain a simpler system. And reduction by stages means that in some instances we have symmetries that come from different nature, and then in that case we would like to first reduce by one group of symmetries and then by another one. So that iterative process of reduction is what we call reduction by stages. And then if we continue, we see that I'm going to explain first what was already done in the case of mechanics. Afterwards, I will explain what is our contribution to the case of mechanics. And in the end, I will say how we can translate these ideas from mechanics to field theory. So just to fix the notation, I would like to do an overview of Lagrangian mechanics. In Lagrangian mechanics, we have a Lagrangian function, which is a real function that is defined on a tangent bundle, which is going to be our configuration space. And then we are going to define an axiom. This axiom is going to be defined for curves in our configuration space, which is Q, and then we fix these points, Q0 and Q1, which are the endpoints of these curves, and then we can associate a number to each of these curves, which is the axiom, and it's just the integral of the Lagrangian along the lift of this curve. So when we have the Lagrangian and the axioms, then we deform these curves, which means we have these deformations over here, and for the parameter equal to 0, we get the curve again, and the variations are the derivative of these deformations for that parameter. So, yeah, sorry. Okay. So we have a variational principle that is going to state which are the curves that have physical relevance. So the Hamilton variational principle is going to say that these curves are those for which, for these three variations that we have here, they are a extremal of the axiom. Okay. And well, this variational principle is equivalent to the Euler-Lagrange equations that we all know. This equation over here, even though it has partial derivatives here, it's written in an intrinsic way because we can choose always a connection in Q to define this horizontal derivative, and then this is a vertical derivative on the tangent bundle. So this is, all the objects here are intrinsic. Well, the Euler-Lagrange equations do not depend on the connection that we choose to write this intrinsically, so everything is fine. Well, so now we are going to reduce this image with the axiom of a group G, which is going to be the group of symmetries of the system. So we have a Lagrangian, which is G invariant, and then we can define a reduced Lagrangian, which is in the quotient of the tangent bundle. I haven't said that, but the group is going to act freely and so that we are going to, and properly, so that we are going to have a nice quotient here. It's going to be a manifold again. And we can define a reduced axiom. And if we study the reduced space of this tangent bundle, what we can see is that it's no longer a tangent anymore, So if we use a principal connection in Q over Q times G, which is the space in which we are reducing, then we see that the quotient of the tangent bundle is the tangent of the quotient manifold plus this term here, which is the adjoint bundle. It takes into account what is the velocity of the particle in the direction of the symmetry. So we have to take into account this term. And this is a fiber bundle, in case you don't know, that the fibers are just like the Lie algebra of the group we are using to reduce. Okay, so with this, with identification, we are going to reduce the problem we had before, the variational problem we had in the unreduced system. So before, we were considering curves in Q with endpoints Q0 and Q1, and the variations were free. But in reality, we were using these curves to plug them into the Lagrangian, which is defining the cotangent bundle. So in reality, we were using the lifted curves in the tangent bundle that comes from these curves in Q with these fixed points. And the variations are those that, of these curves that are obtained by lifting these free variations. So now, if we want to study the reduced problem, we need to take into account the classes of these curves in the tangent bundle and the variations. So if we use the isomorphism we had before, then the curves that we are going to consider in the quotient of the tangent bundle are these ones over here. So we have one part which is a lifted curve, which is defined in the quotient manifold with fixed points S0 and S1, which are the projection of the Q0, Q1 we had before. And then we have this curve that is defined in the adjoint bundle, and whose endpoints project to the same S0 and S1. And if we consider which variations are rising for this curve, what we do is that we take a deformation of the curves we had here, then we consider the class, and then we derive to obtain the variations. And variations are no longer free. So for the first part, the part on the tangent of the quotient manifold, we get again free variations. But for this second part, what we get is a variation of this way, which has three terms. This is just the lift of the other variation. So we can focus only on these three terms. And well, this is a curve in the adjoint bundle, which is arbitrary. So the variations of this curve in the adjoint bundle are going to be obtained in this way. And this is the curvature of the connection that we are using to reduce the A connection I used before. Okay, so now as the variations are no longer free, the reduced principle that I had before, the variational principle that I have now, the reduced variational principle, is going to be equivalent. No. Okay. So now, as I said before, since the variations are no longer free, instead of getting Euler-Lagrange equations, we get Lagrange-Poincaré equations. These are two sets of equations, which are vertical equations, which are accounting the conservation of some quantity because we have asymmetry. And then we have horizontal equations, which are similar to the Euler-Lagrange equations, but now we have this extra term with the curvature. Well, so this is the part of the overview of Lagrangian mechanics and reduction. So now we want to do this process several times. And what's the problem if we try to do this? Well, the problem is that we started working in a tangent bundle, but now we are no longer in a tangent bundle. these equations here are obtained using a variational principle for a tangent bundle plus an adjoint bundle. So we have to extend our category. And this is what Tendra, Marsden, and Ratio did. Okay. Okay. So they defined these Lagrange Poincaré bundles, which are whose objects are the objects of this category are these bundles. So that the first, so this is a sum of two bundles. The first is the tangent bundle on some manifold, and the second one is a vector bundle over the same manifold. And we have three different objects. We have a Lie bracket on V. We have on the fibers of V. We have a V-valued two-form on Q, which is this omega. And then we have a connection on V, which is nabla. And we want to have a relationship between these three elements. So what they ask for that, to have a relationship, is that this expression over here needs to be a Lie bracket on the sections of this bundle.
May I ask you,
yes.
if it's, are you sure that it's always the direct sum? Because it seems to be some transitively algebraic rather than just a direct sum.
Well, this is a special case of a Lie algebra.
Case.
Yes.
But in general, it's not a direct sum, right?
What?
It's in general, it's not a direct sum. I mean,
it's a sum of two bundles. Yes, it's a. Well, okay. So, well, these are the objects, and the morphisms are what we need just to preserve these structures. So I'm not going to look for them. So what they did is they said, well, we have an axiom of a Lie group over this Lagrange Poincaré bundle, and if we use a principal connection on this Q, so the group is acting on Q, and then we use a principal connection for this axiom. Then they have a result that says, well, if this is acting by isomorphisms in this category, then we get a reduced vector bundle, which is this one over here, with the tangent of the quotient manifold, the adjoint, and the quotient of the vector bundle we have here. And they can construct a connection, a two-form, and a Lie bracket, so that we have an object in the LP category, so we don't escape the category that we had before when we reduced. So now if we plan how to do Lagrangian mechanics in these objects, so we just have to define a Lagrangian in these objects, an axiom in these objects, and we consider variations for these curves such that they are determined by the structure of the LP bundle, so that we have something similar to what we had in the adjoint case, but now we are using the derivative, the Lie bracket, and the two form that we had in the definition of the LP bundle. So now if we consider these variations, since this has the same form, we can have a variational principle that is going to give, again, Lagrange Poincaré equations, just with the objects we had in the definition of our LP bundle. And why do they do that? Because now they can reduce by stages, since we don't escape the category. Then if now we have a group of symmetries G, which has a normal subgroup that we want to study preferentially, like, for example, N, then we can consider the quotient of G over N, which is K. And if we, in each step of reduction, use if we are careful with the connection that we use in each step of reduction, then they see that the reducing by G is going to give an equivalent problem to reducing by N and then reducing by K. So in summary, what they did is they start with a tangent bundle. They know these two problems are equivalent because they can always reduce by G. They know these two problems are equivalent because they can always reduce by N. And they prove by hand that these two are equivalent. And well, in that article, they ask for one thing, for example, which is, well, they have done this reduction, but they are not really reducing in the whole category they have defined, because they are reducing just in a subcategory, which is the smallest subcategory that is closed under reduction when you start with a tangent bundle. But they ask whether you can do this reduction for whichever object of the category. So we answered this positively. So we had this result that says, well, if we have a variational principle in an LP bundle, such that, and we have a solution of this variational principle, then, and this variational principle has the variations given by that LP bundle, then the reduced problem in the reduced LP bundle is going to be equivalent. So we change a little bit this drawing. Now we can do reduction for any object in the LP category, and we can show the equivalence just by saying, well, I can reduce by G, I can reduce by N, so these two are also equivalent, and I can reduce whichever object, so I can also reduce here, and I get a problem that this problem is going to be equivalent to this one. So I close the cycle, but in a different way. Also, we gave a characterization of these bundles, so we don't have to rely on this bracket anymore. So we have seen that it's equivalent to ask for this bracket to be, for this expression to be a bracket with so it's the same to ask that this is a Lie bracket and ask for these compatibility conditions. So for example, the first one is that the two form I have on Q is going to be closed under the derivative that is going to give my connection on V. So I have this one, which is like a kind of Leibniz product, and then I have this other one, which relates the curvature of the connection nabla with the form W I have here. Okay, so until here, I have shown everything in mechanics. Now we can go to the case of field theory. So until now, we have always been trying to find curves from on a manifold M. So we were working in this bundle, this bundle of R times M over R. And we were always using the tangent bundle because we were in the Lagrangian picture. But for what we are going to do now, we can consider that my tangent bundle here is going to be the first jet bundle from R to M. So in the field theory case, we are going to change a little bit this connection, this bundle. So we are going to be working in an arbitrary bundle. The fact that this is a P doesn't mean that P over M is principal. It can be anywhere, in any bundle. And now we are going to be considering, instead of the tangent bundle, we are going to be considering the jet bundle, so that this jet bundle is sections of M to P up to first order derivative. Yeah, look. Yeah. Now, well, in this setting, we can do Lagrangian mechanics, just as I saw before. We can define a Lagrangian function, we can define the action, variations, and so on. And this variational principle that we use here can be reduced, and you can see it in these two papers. This can be reduced with the same ideas, mainly of mechanics. So now we have sigma, which is P over G. G is the group is going to be acting on P, and P over over sigma is a principal bundle, and here we can have a connection A that is going to give a splitting in the jet bundle, in the reduced jet bundle, that is similar to the one we had before for the tangent bundle. But now we have not the adjoint, but this this bundle over here with the cotangent of M, which is the base space we have here. So now, if we want to do reduction by stages, we have to define a category, as we had before for mechanics, that is closed under reduction. So we are going to define this category. So once I fix a base space, I have this category of bundles, which is just the jet bundle of a fiber bundle over M. And then I have this part over here, so that the V is a vector bundle over P, such that the tangent of P plus V is a LP bundle. So I have defined a new category for reduction by stages, which is in field theory. And I have used the category of that I had in mechanics. But I could forget about this if you are worried because I'm using just the other category I had before, and just forget about the tangent part here, and say that in V I have the three objects I had for the LP bundle related like in the LP bundles I had before. So since I have this result, I can forget that this is going to be an LP bundle, and just say, well, I have V, so that I have these three structures, and they are related like that. So I can forget about the tangent. And then I have, for this category, I can define Lagrangian mechanics, because I have sections, I have variations in a similar way as I had before, which are defined using the objects of the structure in the LP bundle. And then I get the Lagrange Poincaré equations for field theory. They differ from the Lagrange Poincaré equations for mechanics, because now I have, instead of derivatives with respect to time, I have divergence. Okay. So now we have two analogous results to what we had in mechanics. First one, I have an LP bundle in this category for field theory. And if I have a Lie group G, which is acting on this bundle, if it acts with isomorphisms in this category, then I get a reduced object. And here this is again an adjoint bundle, but now I'm specifying the second part of the product, which is P. This is the adjoint plus the quotient of V. And here I know how to have a structure of LP bundle. So I don't fall out of my category. And then I have another result, so that anytime I have a solution of which is J invariant of a Lagrangian system in these LP bundles, then I have a reduced section, which is also a solution of the reduced Lagrangian I can define with the J invariance. So just to finish, I would like to say something, some particularities of this with respect to the case of mechanics, the main one being the reconstruction. So here I'm saying that I suppose I have a solution in the unreduced problem, and then I get a solution of the reduced problem. But if I have a reduced solution, do I have a solution of the unreduced problem? And this is not always the case. In mechanics, I always have this unreduced solution, but now in the case of field theory, I don't have always that solution. I have to use I have to take into account the holonomy of the bundle and then also the flatness of a certain connection that I can define from the reduced solution. I would like also to say something about what is this reduction by stages. So in the article we have of field theory, we have shown an example which is based in an example of mechanics, which is the rigid rotor, the rigid body with rotors. So we have a rigid body which was configuration space is SO3, and then we have 3 rotors in the principal axis of inertia. So we have in our configuration space also S1, S1, and S1. And this has 2 different sources of symmetry, because we have the symmetry of the rigid body, which is SO3, and then we have the symmetry of the rotors, which is S1, S1, and S1. And if we consider, instead of just one rigid body, we a continuum of rigid bodies, like for example in some molecular strand, we can have an example of reduction by stages in field theory. Well, in the article we have on arXiv, we have also studied the nether current. So, well, I haven't written anything here because I thought I wouldn't have time, but since I have a little time, I will say that in the case of mechanics, you can see that the nether current that you use, that you get, well, that you can define, is going to give the equations of the vertical part, which are related with this adjoint part. So here in this category, then you start just by having horizontal equations and vertical equations. But if you define here another current, as you would like naturally do, then the equations of these, the vertical equations that you get in the reduced problem are defined in this bundle. If you just take those that are in this part, these coincide with the nether current that you had defined before. So it's going to be saying what are the new vertical equations that appear in each step of reduction. So this is more or less what I wanted to say. I have some references here. This one is, the last one is the one I have used for the Lagrange Poincare reduction in field theory. This third one is the one of Sendra, Marsden, and Wright that I've been mentioning throughout the talk, that introduce Lagrange Poincare bundles. And these 2 are articles that are going to appear. That is the content that I have explained here, that is our contribution. Okay, so thank you very much for your attention.
Thank you. So let me maybe does it work? Does it work? Yeah. Let me first ask you the following question. So at the very beginning, you're doing what, if I understand correctly? You take a manifold on which any group is acting freely.
Yes.
You take the quotient is a principal bundle, so everything is fine, right?
Yes.
Then you take T of this manifold, the configuration space, take again the quotient. Right? Is it correct? So what you get is it's called the AT algebroid of this principal bundle.
Yes.
And then if you have a connection, this gives you a splitting. But in general, what you're doing is, it seems that you're doing some mechanics, but instead of the tangent bundle, you consider transitively algebroids, right? Is it correct, what I'm saying?
Sorry, the last
You are
part?
doing mechanics where instead of T, the tangent bundle, you consider transitively algebroid. Is it correct?
What?
And the category is the category of transitively algebroids. Is that true?
Okay.
Yeah. So did you consider more generally algebroids, say, than the foliations would be involved, for instance?
Well, I haven't considered how to see this as a Lie algebroid.
Okay, okay.
So I know this is a so in the when
yeah,
you are in the
if you have a connection, everything splits, and you get exactly what you have here with the curvature and all this stuff, of course. But without connection, it's called the AT algebroid of a principal bundle.
Yeah, the T algebroid is this special case. Yes, when we have
this.
this.
Yeah. All this.
Yes. So
without splitting.
Yeah, this is with the splitting. So just we change this part to be any other vector bundle, but
okay, maybe we'll discuss it.
Okay.
So, are there any questions? Yeah.
Yes.
Yes, I have a question. So I have a perhaps naive question about this Lagrange Poincare variation.
Okay.
So how does it work? So in a normal one, you'd set the variations of positions to 0 at the endpoints, whereas here you let them be free and you don't tell the velocities they have to vanish at the end.
No. In this variational principle that I have in the reduced variational principle, I always say that the points are going to be fixed. So here, this curve that I use to define the variation of the curve I have in the adjoint has to have the points fixed. So that condition is always even in the Lagrange Poincare equation. What changes is that now, since I have the splitting, the free variations I had here, free in the sense that you can variate, but when I say free, you can variate the curve, but the points, the extremal points are fixed. So these variations that were free here, when you consider them in the quotient, they have this second part, the part in the adjoint, which is has this particular form.
And these are the equations you get from varying some functional again.
Yeah, so then you will variate this functional. So now the only change is that you have you don't have all the variations. So you get different equations.
Okay, other questions? Remarks? If no, let's thank the speaker again.